So this talk is a good follow-up to Vincenzo's talk that we have yesterday at the end of the day. So with Vincenzo, we started looking at mechanical property of system, right? The first example he showed us, it was a biological system. So nature created a system, and Vincenzo was trying to understand why we were observing given behavior, right? Interesting behavior. Now here, we'll take a different perspective, and we'll try to engineer systems. So we'll try to engineer interesting behavior into a mechanical system. All right? And so this system, this day, with this interesting mechanical property, goes under the name of mechanical metamaterial. And so what are mechanical metamaterial? These are carefully structured systems whose behavior are governed by geometry. And what we are trying to engineer are interesting, unusual behaviors. Now, something I've been doing over the years is looking at the nonlinear behavior of this system. So we deform this system a lot, and nonlinearity arises. And then we are trying to exploit this nonlinearity, this instability, to enhance the functionality. And here I'm reporting a few examples of work that has been reporting in this area. So for example, you can use, what has been shown is that you can use napping and instability to program the response. So you can have different stiffness depending on how you snap. You can have shape morphing. This is work by Itai Cohen. So you can have structure that can change largely their shape. You can also use this strategy to manipulate the propagation of waves. In this case, this is work by Chiara D'Arraio Caltech. They got unidirectional propagation. So the waves can only go one direction. All right, so in the past 15 years or so, the community, we became quite good at designing a nonlinear system capable of a target functionality. This is work by Martin Van Ecke and Corentin Coulet, who last year was here, is not here this year. And here what they did, they programmed this cube, they designed this cube, and they assembled in such a way that when you push from the top, a smiley face, you see, a smiley face appear. Good. So now the question we start asking is, okay, can we also program more complex functionalities? For example, can we start to program also interaction with the environment? So here what you see is a strip, is twisted, and is made of liquid crystal elastomer. And there is no sensing, there is nothing. It's on a knitted plate. And now what you see is when it bounces an obstacle, it's turning around. And so it's not getting stuck. And this is because when it snaps, so there is an instability, it's basically it snaps, and then it starts rolling in the other direction. And this is work coming out for North Carolina State University. Now it's 3 years old. And we started also in the past few years, we have been thinking about along this direction. And so today I want to show you 2 strategies that we explore to, create systems that can interact with the surrounding environment. And first we'll be looking at multi-stability, and second we're looking at more classical metamaterial and try to use inverse design to encode these functionalities. All right, so first project I'm going to present is work led by my student Leon. And so what is the goal here? Here we are inspired by system like this one, 2 very different systems, one engineer one biological one. There's a structure that move, and then they sense obstacle and they move away from them. One is highly engineered. The other is a biological system, unicellular, non-neural, so there is no brain, and there is no neural system. And our goal is to realize a machine that can do that. Move, sense an obstacle, move away from it. And what we would like to do, differently from the Roomba, is to not rely on traditional computational architecture. So limit the amount of sensor and electronics that we need. Do it in a mechanical way. All right? So here is our starting point. It's a 4-bar linkage. It's a very simple structure. You have 2 bars and a bunch of ball bearings. Very good. So now what we do, we want to introduce elasticity, right? We want to play with mechanics. So we introduce a rubber band. And now an interesting feature is by just changing how we anchor this rubber band, we can largely change the behavior. You see that basically when we switch the position of the band, we switch from monostable to bistable. Now you see the structure is stable both up and down. when the rubber band is attached to the other point, it's only stable when it's in the up configuration. So an interesting feature of this system is, and that's why we chose it, we can easily manipulate the energy landscape. The system is very, very simple. So we have two levers that rotate, and then we have a linear elastic band, so we can write down the energy. And, and then we can compare the experiments with the model. Everything matches. It's a very simple system. And again, the interesting point, and that's the reason we eventually landed on this system, is that by changing the position where we anchor this rubber band, we can largely change the energy landscape and switch from monostable to bistable. All right, very good. So then what sort of game can we play? Well, we can start stacking a bunch of these units. And then, let's say we define a state 0 when the unit is down and state 1 when it's up. All good. So now, if we stack 2 units, we have 4 states that are available, right? 0, 0, 0, 1, 1, 1, 1, 0. Now, typically, at least in mechanics, we care about the 4 stable states, and we try to attach a functionality to each state. But here, instead, what I'm going to mostly care is about how I transition between the states. So how do I move, when I apply a load, from which state to which state I'm going to go, and then which one is the next one? All right, and let's see how this works. So here are 2 units, and now we connected the spring there. And now we start pushing on it. And so this is the energy landscape. Again, I can predict it analytically. And now, I start moving the last unit up. And so I follow the minimum energy pathway, right? So in this case, I go horizontally. I go to 1, 0. And then I keep pushing. And at this point, I go vertically up to 1, 1. And now I start pulling down. And the question is, which way do I go? Do I come down vertically, diagonally, or along the horizontal? In this case, it's energetically less costly to go to 0, 1, and then to 0, 0. All right, so I do a loop. I circle between the states. But now, if I change the position, it used to be up there, now it's here. You see that the energy landscape is very different. And now, when I do the same game, I'm going to go up and down, first up, and then horizontal, and come down the same way. So bottom line is, by changing the position of the rubber band, I can control how I travel between states. And we can map it out, quite nicely. OK. So then, probably at this point, you're asking you promise us a machine that moves. Where is that, right? So far, we have a mechanism, 2 degrees of freedom, and 2 degrees of freedom that can do certain sequences. So next, what we do to get the machine, we attach legs, V-shaped legs, to the mechanism. And we attach them in such a way that when I move the outer block, the legs go up and down. And when I move the central block, it goes back and forth. All right, what does mean, because of the way we attach this leg, is if I loop through the 4 states in one direction, I do a backward. So if I do 0, 0, 0, 1, 1, 1, 1, 0, I do a backward step. And if I travel them through the 4 states in the other direction, I do a forward step. And now, I can, OK, so this is the bulky machine, and this is real time. You can see it's not particularly fast. And now we program, we position the anchoring points so that both of them travel through the cycle in such a way we do forward steps. And you see this machine moves. Not particularly impressive, but it moves. Now we can change one position of the rubber band on the right side. And now one side wants to go step forward, the other do a step backward. As a result, it's rotating. OK, it does what expected, not particularly impressive, but it does it. Now, I think despite the fact that this machine is not impressive, there is an interesting game that we can play. And this is the game. So now what we can do, we can decorate this machine with some antenna. These are levers. And now you see what's happening when Leon is pressing on the antenna. The antenna, we move this point. We move an anchor point of the rubber band on the opposite side. Now, What we learned through so far is that when I move the position of the rubber band, I can tune the cycle. I can change the cycle. So now the idea is, OK, I'm bumping into an object. I'm changing the cycle of the opposite side. So if I program everything right, I should be able to turn away from an object. And let's see if it works. So this you can see the machine. So now the left antenna bump into an obstacle. And so it's changing the position of this anchor point. And we carefully program, we chose the rubber band the position so that a small change in distance switch the direction of the cycle. And so now the machine frees itself. So it's not only a cylinder, now we have a V-shape, keeps going. And now when an antenna bumps into it, change the direction, it travels through the state on the opposite side, and is able to move away. And this machine, there is only one linear actuator that keeps moving back and forth. There is no other sensor, nothing else. 3 obstacles, go the left, the right, then the left, then the right. So the game is quite robust. It keeps going. And then one more example. This is a sort of a maze. And there are a couple of walls. And this guy slowly finds a way out. All right. So we got quite excited because in a very simple way, we were able to program interaction with the environment.
So is there any geometry where it's just going to be in a cycle and going sort of back and forth and not moving?
Yeah, so there are some. So if the V shape is very, is very, very sharp, there is a limit, right? Given the size of the machine, eventually it's bouncing back and forth. One thing you can also do, and we did, you can also introduce an asymmetry, so a preference to always rotate. But then this is work only for specific type of environment, right? Yeah, this is, clearly if it's a very sharp V shape, eventually it keep bouncing and it cannot really, rotate 180. But it's, I would say, fairly robust. There are also an important interaction we need to account is the interaction with the ground, right? So this is a fairly, slippery surface that now is navigating on. You can tune those interactions by tuning the rubber band. So, if there is more friction, then there is more force coming from the environment. So the idea is I need to put more elasticity into the system, right? So getting stiffer rubber bands help. All right. So then where are we going next? Clearly, this is a bulky machine and it's low, but we were excited about the concept. And now we are trying to get this concept, and what we are trying is also introducing in a system that is easier to realize and hopefully also to miniaturize, because in, for example, microrobotics, there are challenges because the current microrobotic, and this is a hammer, is considered sort of state-of-the-art in the microrobotic community. Typically, this system has tons of actuators. Each single degrees of freedom requires an actuator. And this requires a lot of control and a lot of sensing. So I think these ideas, not in the form I show you, but in a different version, could be helpful and maybe could alleviate some of the challenges here. So we'll see. All right. So now into the second part. So in the first part, we were sort of smart in designing a structure with a very tunable energy landscape, and then we took advantage of that to program interaction with the environment. So we have also used a different strategy to program interaction with the environment, and through inverse design. And specifically, the work I'm going to present is work led by Giovanni, who's back there in the room, and also collaboration with Vincent, who's also down there. All right, so this is what we have applied. We have been applying inverse design to a prototypical class of mechanical metamaterial. These are the one based on the rotating square. Last year, we presented with Bob, and it was on this class of metamaterial. Last year, we were looking at the case where we have a cagome lattice, so where there are triangles connected. Here is mostly, we are going to look at squares connected at the vertices. And the initial concept is now 25 years old, and initially people got excited because this system showed negative Poisson ratio. So you push in one direction, you contract in the other. So, and in the ideal version, the Poisson ratio is -1. Now, then 15 years ago, we started building this system. So now, in the idealized version, you have perfect hinges. These are impossible, very challenging to fabricate. So you replace that with shims, with thin, flexible element. And this, when you press on them, when you compress it, eventually they buckle, and they induce this rotation. And you can also fabricate a task kirigami. So you fabricate by introducing an array of cuts in the close, and then you pull on it. And this system has also interesting wave propagation behavior. For example, with Vincent and Bollé, now almost 10 years ago, we showed that it supports the propagation of solitary waves. All right. Now, a point I want to make about this system is, by changing the shape of these blocks that are connected at the vertices by ligament, we can largely change the behavior of the system. So here you see two systems. This is a regular square, array of squares. This is, we have a supercell. We have 4 irregular quads. The hinges connecting these different units are all identical. And now what happens when we compress, you can see here the stress strain curve, the force displacement that we record is very, very different. This case is pretty much linear. This case is initially linear, and then there is plateau because of the instability. All right, so what we learn from here is that the shape of this unit plays a huge role, even if we keep the topology constant, right? We have 4, we have 4 node vertices, and we connect them to the neighbors. And then, then you open up a question is, how do we explore this design space? And there is beautiful work by Maha, my colleague Maha, that roughly now 6-7 years ago, implemented this optimization algorithm to identify structure capable of moving from shape A to shape B. So the question he was asking is, okay, I want to move from a circle to a square. Which shape should this unit have? Now, in the way you look at the problem, you consider a mechanism. So this is a 1 degree of freedom mechanism. When you rotate one unit, you impose pretty much the rotation of all the other units. The hinges are perfect. And what you're imposing are geometric constraints. The fact that there should be an overlap and everything should match. All right. But then, when we really realize this system, and this is a picture again from work from Corentin Coulet and Martin Van Ecke, you see that they behave very, very far from the mechanism limit. Mechanism limit means I rotate a unit, all the other units rotate by the same amount. And now here you see there is an indentation there, so a force is applied here. And you see how quickly the rotation decay because of elasticity. Unfortunately, we are not very good at designing these hinges, right? So there is some elasticity, and the elasticity clearly plays a huge role. So then the question, you can ask us, okay, very good. So first of all, we need to account for elasticity if we want to, eventually identify systems that we can fabricate and behave the way we want. And second, maybe this also opens up opportunity to use this elasticity, right? Because maybe, we can use this elasticity now, this decay also for sensing. So maybe, I can use for sensing capabilities. And so, can we exploit elasticity also to program, interesting functionality into the system? All right, so first of all, now we need to be able to model elasticity. And, the old days we were doing full-scale finite element simulation. You can do that. The problem is, it's highly nonlinear. Every simulation takes half an hour. They are very accurate, but takes forever. Then the question is also, do we really need to go full-field finite element? Because if you pay attention to the movie we were looking before, all the deformation is just localized at the hinges. The units pretty much behave as rigid body. And so then, maybe we can go away with a simplified model where we have rigid bodies connected by springs. And the idea is, I can have a combination of springs, one that picks up the stretching, one that picks up the shearing, and one that picks up the bending. And, so we have 3 springs, and then, you can write down the equation of the motion. You pick a unit, and it's a mass spring network. And you write down the equation of motion. You consider all the forces arising from these three springs and the interaction with the interaction with the neighbors. All right, and so here is how they look in the specific case of a square, for a square grid. And the only thing is, we are accounting for large rotation and large deformation, so you need to be a bit careful with trigonometry and accounting properly for rotation. All right, and then how it works is you have the equation of motion, you have a system because you have mn unit. For each unit, you have three equations, and then you numerically integrate them, Runge-Kutta, Euler-Forward, pick your favorite. And then you look at the response, and the question is, does it work well? So here we have a comparison between the experiments and the model for a regular grid, and we see that once you calibrate the spring, so the trick here is to calibrate the spring. But if you calibrate the spring properly, then it seems that this model can capture what's going on in reality. All right. So then you can start it. Roughly 5 years ago, we started playing the game. Okay, so now I have a model. It's not taking anymore an hour. It's taking 2 minutes, 3 minutes to run, right? In the original version was implemented in MATLAB, OD45 to integrate, so 3 minutes roughly, you can get the behavior. So now I can start asking the question, okay, can I identify system capable of a given behavior, right, that I want? And as initial exercise, we focus on stress-strain curve. So I want a system that gives me this given stress-strain curve. And so what we were doing at the beginning, we were inspired by machine learning, and so we have a neural network. So we create a database. We run many simulations at the beginning for many systems, right? And we collect the stress-strain curve. And then we were introducing a surrogate model, a neural network that was acting as a surrogate model. And then we were using that, so we were picking some curves from the database, slightly perturbing them, then evaluating very quickly through the neural net the response, and then picking sort of an evolutionary strategy, gradient-free, very simple gradient-free algorithm. And eventually we were getting some good result, picking up the result, and then verifying by the discrete model and by experiments. This was what we implemented roughly 5 years ago, with Bowley. And so just an example, so we pick, let's say, this stress-strain curve. This we would like structure that basically give us this mechanical response. And then, you look into your database and you pick up, the closest one, and you see that, okay, we are almost there, but not really there. Can we get better? And then, you run the algorithm, and you find something that is much closer to the target. But then there is some error introduced at the fact that we were using a surrogate model that is not really the physical model. So then what you do, you run the physical model, and you get the discrete model, and you get some curves that are nearby. You pick one, and then you fabricate it. So these are the fabricated sample. And, you see that you're able to recover, get very close, to match very close the behavior that you wanted to program into the system. So this was a success story, but there were also strong limitations in what we were able to do, because this was gradient-free optimization. There was a neural network doing a surrogate model. So for example, you see that what we do, we take a 2x2 unit, we move it around, we change it, but then we tessellate it. Because so there's 4 units, 4 vertices, 2 parameters per vertex, so 32 sort of parameters that we were able to change. Going above that, it becomes pretty much unfeasible, because you're gradient free and you don't know how to handle that many variables. So it was sort of a limitation. We were running against a wall. So then we started looking into a new strategy, and this is when Giovanni started playing key roles. And we start looking into, Vincenzo yesterday gave an introduction to us. We started taking advantage of this tool developed in computer science that implement automatic differentiation. And automatic differentiation now enable us to use the gradient, and so to do gradient-based optimization. All right, so same system, same discrete model as before, but now we can use automatic differentiation even a little earlier earlier to simplify our life. So, we have a system, we have a bunch of spring, rigid body, we can write down the energy. And now we can take advantage of automatic differentiation at this level. And instead of doing the, sort of boring and very careful and long exercise of deriving the equation of motion, we can use automatic differentiation to do that. Writing the energy is order of magnitude easier than writing the equation of motion. And then we can take advantage of the automatic differentiation to get the equation of motion. And then same story, then you do a forward solve. Basically, you numerically integrate. And the response will depend on many parameters, the geometry, the springs, the initial condition, the way you load it. And now, what we can do, we can use a second time automatic differentiation. We can take derivative with respect to whatever parameter we want. And then this means, and specifically, we are focusing on geometry, right? We are focusing on the shape of these units, because this is a parameter we can easily manipulate in experiment. Changing the spring is very challenging in experiment. So, getting a target value of stiffness that, the algorithm identifies. So we change the geometry, and then we can go gradient based. If you're curious about the specific tool we are using the one coming out from Google, JAX. But there are many versions of, library that implement automatic differentiation. All right. So now, how does it work? Here is a toy example. So now we have a grid, 24 by 16 of units. We clamp the corner. We apply a pulse here. And now, the goal is to say, I would like all the kinetic energy to be routed into this region. All right? And so what's the goal? The objective is to maximize the kinetic energy in that specific region. And then what is design space? Now, differently from before, where we were designing only, a 2x2 block, and then we were tessellating, now we are designing every single quad independently. So we have order of magnitude more degree of freedom, and gradient-based optimization. Specifically, here we are using MMA, method of moving asymptote. And there are constraints, both imposed by fabrication and by the fact that, geometric constraint you don't want to overlap. And all right, so here is how the algorithm eventually evolve the geometry over iteration for this specific problem, for this specific boundary condition and this specific target. And what we see is eventually land on a configuration when we have 4 large units over there. And it's largely aperiodic, but we see also some region where we see some repetitive, motifs. And now what we can go next is we go to the lab and we fabricate it. Now, this looks very different from the green structure I showed before, but pretty much, they are identical. So now, before...
These are non-linear,
These still nonlinearity. So they are still nonlinear, and the nonlinearity comes from mostly is large rotation of these blue things. These blue things now are plastic shims, and the white blocks are a PLA, so 3D printed. So before we had green shims, the sample before were casted. The problem is when we cast the sample, there is a minimum width below which you cannot go, because when you demold, you just break. And also the green rubber then is fairly viscous, so there is some viscoelasticity. So when you do this more dynamic, so you send a pulse, the viscoelasticity is a bit too high to really get a decent propagation of waves. So we went, and this is also much lighter, so we can suspend it, and we don't need to worry about friction. So there are a lot of simple design consideration going in, but eventually we landed to this. And so these are plastic shim, and they bend a lot, so it's still nonlinear. They still bend quite a bit. All right. So, and then, you see there are large rotation if you look locally, right? The blocks are rigid, but still at the hinges. And now here is a comparison between the fabricated structure, and here is the simulated one, where we apply the same input, and we see, again, we have validated the model before in a static. For uniaxial compression, here is more dynamic, but we still see that the model, in the experiment, we get what we were supposed to get according from the computer. All right.
Your optimization
It's
not on the fly.
It's not on the fly. It's not on the fly. So first we run simulation in the computer. Eventually they identify a structure. In the code, there are constraints based on fabrication. So for example, the length of the edges. We want to be a certain minimum. Otherwise, then we have hinges that are too close, and this creates many issues. Also the angles. We don't want angle to be too sharp because, again, fabrication issue. So there are fabrication constraints in the optimization, but yes, it's not that we fabricate, we test, and we keep doing the loop. No, we do all the optimization in a computer, and then when we find a design that we are happy with, we move to the lab and we fabricate it. And yes, so then, going back to before we have this machine moving, we can also think about maybe, for example, using this strategy for motion conversion and say, okay, now I'm applying a linearly polarized input here. Can I have this architecture work in such a way that it converts that into a circular motion, spinning region here? So, can I also use this, for example, for motion conversion? And so, you do. And how do we do that? What is the objective in this case? Well, in this case, we want to maximize or minimize the angular momentum. And if we minimize, we're going to get a clockwise motion. And if we maximize, the idea is we're going to get a counterclockwise motion. And OK, so here you can see the output, 4 different simulations. So we are loading at the same location, but here we are maximizing and minimizing. And here, where is the loading applied? The loading is here. So different location, a different target region. And so this is in the lab, but then, we can also get them real. So in this case, what we ask for, now here I show you only the experiment, but what we ask is this circular motion to be at one of the units at the boundary. So now what we have on the structure is a linear actuator up here. The linear actuator goes up and down. And now the structure is designed in such a way that it's transformed this linear input here to a rotational motion here. And so this enables, we have basically a gate, right, a walking gate. And so these guys move. And here is where we are. I mean, very preliminary, but then going back, making an analogy with what I showed before is okay. Can we also, in this case, tune the gate, right? So for example, can I change the frequency that I apply to tune the gate? So I want to go clockwise and then switch to counterclockwise. And even better, instead of me changing frequency, maybe can I do this switch automatically when I bump into an object, when I got into contact with an object? So this is ideas that we are bouncing around and toward which hopefully there's going to be some progress.
When you are using your actuator, can you program the way that you are, sending in the impulse, or somehow it is frozen how you are sending the impulse via the actuator?
So right now, these are optimized for a specific input, if that's the question.
Yes, but can you change this somehow on the fly or not?
Yeah, I think this can be on the fly, and you can think about, so what we see is that typically they work over a range of inputs. But you can, if you have a couple of inputs, you can, on the fly, you can also think about optimizing for several inputs. So now this is optimized for a specific input, but you can also optimize for a set of inputs. So that then you can vary.
In an integrated manner at the place where you are having the actuator have, I don't know, some piezoelectric element or some sensor that it could, so to say, sense the response of the structure at that point?
Sorry?
Could you use the mic?
The mic.
What I was asking also, it is at the point where you are having, so I understand that you can change the way that you are sending the input signal via the actuator. What I'm asking is, can you at the same point have a sensor that it can measure the response of the structure to the actuation?
We'll get there. So hopefully, okay, be patient, a couple of slides, we'll get, yeah, we have been thinking about this. And let's see, give me a couple of slides, and then the question is not answered. Let's go back to that. But I show something. Yeah, we have been thinking along those lines, exactly. All right. So then the question, yeah, it goes along exactly. Like, can we also sense? So now we are putting in an input. We are getting some deformation. Can we somehow sense what is going on, right? So that's the question exactly we started asking. And so, for example, can I have as a sensor, can this system compute its own shape, right? So I can figure out how things are moving around. So, all right, so, I have my structure here, and, let's say I apply a deformation from the top, right? I have my actuator that, are pushing down from the top. And then what I expect is eventually, this will lead to some deformation. And, each unit, the deformation of each unit is described by 3 degrees of freedom, displacement x, displacement y, and there is a rotation. And then, the question is, if I put the sensor, right, how many sensors do I need in order to sense? And, is there a position that is better? It's also, and these are all work in progress, so I wish I had answer for those. I'll show you where you are, and I'm very, I'm looking forward to inputs also. So, and then the question is there also an architecture that is better than the other? So is there a geometry that works better than another geometry? Is there the sense is maybe I need some nonlinearity, which type of nonlinearity, what is it needed, right? And all right, and the idea is, okay, can I, for example, take the information about the deformation, the rotation at few locations and linearly combine them in the simplest possible way to get eventually, to reconstruct the shape, right, to sense what's going on. And, okay, and, then you do a linear regression and, you learn the weights, and can we do this simply? So we started playing this game. And, for example, you can say, okay, now everything is a sensor, right? I'm sensing everything, so I should, this seems to be okay. Can I reconstruct where I am? And the answer is yes. So basically, if I collect all the rotation, no surprise, if I know the rotation on every point, I can also reconstruct the shape. And here, there are circles and stars. So the stars are the centroids of the square on the perimeter, as predicted by the discrete simulation, that for now is the grand truth. And now this, the circle are the one predicted through this linear regression, picking up the information from the sensor that we are positioning. In this case, there is sensor everywhere. But then you can ask, okay, how about, if I put few sensors, right? Eventually, we will like 1 or 2. And now you see that errors start to arise at the corner. You see that the star and the circle move away, but you also see that there are, good region where it's still enough. And then you can push it even down more, and now, 3, and you see even more error, right? And okay, and then you go down 2, and you see more discrepancy. And then, okay, then the question is, okay, there is some there is some positive sign, but it's not too perfect. Now, is the geometry gonna help? And and then you can start, okay, can I define a geometry that minimizes the error, right? Can I define a geometry where by using just this sensing 2 information, rotation at 2 points, and linearly combine them, I can better predict the shape. You can formulate an inverse design. And then again, we are changing geometry. The idea is, okay, can I change the location of this vertex so that I get the best possible sensor? And this is again what the algorithm is identifying. So it's moving the nodes around and eventually finds something. It lands on a design that is, let's see. Okay, this is the design it lands on. And so now you can see, and here again we have 2 sensors. You see that now the star and the circle stay much closer. Now here is where we are right now, but there are tons of, at least I have tons of questions, because it's like, okay, what do we really need if we want to sense, right? If I want to design a structure that can sense with minimal information, what are the important features that I should have? Is there a specific type of nonlinearity? Do I want to be as linear as possible? It's just a matter of correlation, so a good correlation between the rotation I measure here and the rotation of all units. Hopefully, in a couple of months, I have answer. And if you have any input on this, on direction to explore, I will be very happy to talk. And yeah, eventually, we see the optimize. Yes, it works very well. It works well with just 2 sensors. We can sense what's going on. but we don't have much understanding of really what are the ingredients that are needed for this to happen. But then, okay, so we optimize. So now we have few sensors. We can sort of understand if I have, if I sense the deformation of a few locations, I can sort of sense what's going on. And so now the question also we are asking, okay, can we also use that to interact with the environment? And so, now we go back to the Roomba and to the parameters. So can now we use this? Can we use this to basically move? And then if there is an interaction with the environment, to use this information to change the trajectory. So that's what we are thinking of. So, same system. So now we are adding the environment. And the question is, the environment is going to affect, it's going to deform, right? We are looking at mechanical interaction with the environment. So there's going to be deformation. Then we are going to be a readout, right? We read the information a few points. And now can we use this to change the input so that eventually we use the deformation to control this metamaterial? So that's a sort of the, the big idea. So we are not there yet, but I'll show you where we are. So, this is sort of what we did. So this is the metamaterial. The shape, instead of a square, is an annular shape. Good. And now what we do is we put in a drivetrain. So 3 wheels. And now we are looking at interact, then we send it against obstacle. And now what we would like eventually is to use the deformation that we monitor at 2-3 locations to basically control the trajectory of this object. And all right, so first of all, now there are 3 wheels at the ground. And this basically, by the spinning velocity of this wheel depends on the voltage we are sending in. And we can individually address them. So depending on the voltage, they spin at a different speed. And you can characterize that. And then there are interactions with friction, the wheels, the ground. We can characterize that. And now we can put into the model. And and now, okay, if you're the same voltage, top and bottom, 0 voltage here, it goes straight. And it matches the velocity that we see in the lab. And now, if you make an asymmetric, so we put a voltage, turn, okay, everything makes sense. But now, okay, now we also need to introduce the interaction with the obstacle. So now there is going to be contact, right? Also, there are obstacles, so there is mechanical interaction. So we need to expand the model to account for contact. Not only before, in the original version of the model, we have internal contact, where a unit was were in contact with the other. But now we have contact with external object. And, you have normal force, you have frictional interaction. You cook up the simplest possible model. You do a tons of experiment with synchron indentation to calibrate. And, eventually you fit a number of parameters. And then, the way you fit them, and then you verify, you do a bunch of experiments, you do more experiments, and you make sure that eventually you can predict. And here is the experiment. So now we send it against an obstacle with a given voltage. So we set the voltage for the wheels. This is set. And then we monitor the position of the robot in the experiments with cameras, and now also in the simulation. And we try to be there. All right, very good. So now we have a model that captures what's going on. And so now the question is, OK, now can I also monitor? So now the idea is, if I monitor the deformation of the rotation, right, of a few points, then can I use this? And we specifically, we are using all sensors. Okay, you place in some sensor to monitor, right, the deformation of a few points. You could also use a camera if you want. And then the point is, OK, can I provide a linear feedback to the motor forces? So I change the voltage provided to the wheel. And can I do this in such a way that eventually then this object is able to navigate in the environment according to, in the way I want? And all right. And so, for example, let's say, we would like this object to move straight. To go, despite the obstacle, it's going to run in, just go straight. And, so you want to maintain the straight direction motion. So basically, you want to minimize, when it's coming in, then it's going out an angle. You want to minimize this angle. All right, so you want to minimize this angle. And then, you do training with many, you basically what you do, you change, you look at the deformation of 3 locations, and then you find the optimal weight, right, that eventually minimize this angle of which after you come out from the obstacle, this angle theta. And all right. Oops. OK, and so here is sort of what we see that is not particularly great. So what we see is this, OK, this behaves, but these ones are not particularly good. So we get mixed feelings. So for certain starting position and certain interaction with the obstacle, it seems to work. For other, not particularly well. So then, OK, then the next question is, OK, how about if I also modify the geometry? What we learn is that, OK, modifying the geometry helps a lot with this sensing. So now we can start, how about if I modify at least the geometry around the sensing areas, right, where I place my sensors? And so, you know, you do, again, in this case, they're also modifying the geometry there. And, you know, the way we do the optimization is we send this metamaterial against many, many obstacles, different size in different locations. And then, OK, what we see is that when here we are only optimizing the weights. Here we are optimizing both weights and geometry. And we see that we can send the error much lower. So it seems that the geometry helps. And now here is, yeah, where, you know, now you can see that now this one used to go up at 90 degrees. Now it's going much straighter. So it's working much better. And eventually then you can play games and where you send it through a sort of an obstacle course. And now there are many obstacles. And we see that in the computer is doing a good job. Now the question is, you know, do we see this also in the lab? And I wish I had an answer for you. So, OK, we can also, you know, we were straight. You can also think, OK, I want to write every time I bounce in an obstacle. You can change the policy. You can change the policy. You're not only limited to go straight. But, OK, so now in the lab, this is something we're working on. And yeah, Giovanni has been fighting against sensor and everything else. But I believe now we are in the last round of what we believe to be the last round of iteration. We identify a couple of issues that we have fixed. And so hopefully now we can see the behavior. You know, we can do obstacle courses on the lab and see promising. I mean, realize this promising behavior that we have seen in the computer. Yes.
I guess I'm not sure I understood. Earlier, when we were training your design, the neural networks.
Can you use your seat mic, please?
The gradient-based system was used to design what I would call the reference structure, and then you tried it. But here with the controls, you're changing the geometry in real time. Is that right?
No, we are not changing. No. Also in this case, the training is done in a computer before.
Before, OK.
So before. So what we do is we did a lot of experiment early on to characterize, because we need basically to characterize the contact, frictional interaction, and we need to characterize the ligaments, right? So these need to be representative of what we see in experiments. So and we are not going to modify those during the optimization. So we do a lot of experiments at the very beginning to characterize the parameters. Then we run in the computer. And in this case, we optimize both for the weights, so how we linearly combine the deformation that we read out, and the geometry.
So what the sensors, the way the sensors improve this process is they give you more information about what the structure is doing.
Yes, exactly. And now, Bob, we don't have an understanding. If you ask me, OK, good, the algorithm identify a structure that does this. Which features are important? Is it because it's more nonlinear? Is it because it's more linear? Is it because it's more correlated? There is a better correlation between the deformation here and the deformation there. This is a question I wish I had an answer, but we are currently exploring. Hopefully, I mean, but yeah, are the current questions we are asking. Mm-hmm. All right, and that pretty much, yeah, my concluding slides. And yeah, and you know, we got excited about programming interaction with the environment, and you know, and incorporating in this system also the ability to sense in a very rudimental way. We are still very far from intelligent system. There is no memory. There is no learning. At the moment, we are just programming a functionality. But there are motivation to keep moving forward step by step. And 2 papers that for the 2 system I show. Lastly, for the last one is work in progress. Thanks, and happy to take any question.
Thank you very much, Katia.